Good evening. I'm going to be going over flip-flops, slash registers, slash whatever you want to call them, and the math libraries. So first thing we'll start off with is if you want to use let's just start off with math libraries in general. So if you want to use the newer libraries, which I highly suggest you use, simply just uncomment that. The numeric libraries are very nice, and you should probably be using them. So first, let's create some signals. This is just an example, so there aren't going to be any I/O ports or anything like that. So you have your input. For example, let's say we have two inputs. And one output. Okay. So obviously we're going to be assigning to output, but how do we actually do the addition? There are a couple ways. First, the numeric libraries have signed and unsigned libraries. So, or signals, pardon. So you want to decide if you're going to use signed or unsigned. For this example, I'll be using unsigned. You could use you could use signed also. This is just for the example. So since VHDL is strongly typed and initially these inputs are standard logic vector, we need to convert them to unsigned. So you can do unsigned 1. So this will use input 0 and 1 as unsigned, and we'll add them. And what is produced from that addition is an unsigned number. So since output 0 is standard logic vector, we need to convert that to a standard logic vector. So in this instance, you'll have two input vectors, an output vector, and they are all standard logic. So you have to say, hey, this is an unsigned vector, then plus another unsigned vector, which gives you an unsigned vector naturally. Then you have to cast that back to standard logic vector. Now, for a different example, one too many. Let's have 2, 3, and 1 here. So let's assume your inputs are actually unsigned. So you can do something like this. And it will assume, well, it won't assume, it knows that they're both unsigned numbers. It will do the addition for unsigned bit vectors, and it will produce a unsigned value. So since output 1 is standard logic vector, we'd have to convert it back. not converted back, converted. So this is completely acceptable. You have unsigned vectors. You're adding them, then you have to convert it to unsigned since output 1 is unsigned. For the reverse, it's really quite simple. Since output 2 is unsigned, we don't have to worry about doing the standard logic vector before, so we just have to convert the inputs to unsigned. I cannot type on my own keyboard today, so converting the standard logic vectors to unsigned, you're adding them, and then you're assigning them to an unsigned signal. Completely A-OK. And now for the last case, which is probably the easiest out of all of them. Simply have unsigned for everything. And I need to change these values real quick. So, since everything is a unsigned vector, all we have to do is input 6 plus input 7. And that will do what you want it to do. You're taking two unsigned vectors, you're adding them together, and you're assigning them to another unsigned. So that's hunky-dory and all good and all that fun stuff. So if you're doing a lot of math and everything, it makes sense to use unsigned. Or not unsigned, signed or unsigned. If you're just doing something real quick, maybe just convert it and then convert it back. It depends on what you're doing and, how easy it would be to code, basically. So just be aware that you can do these lots of different ways, and obviously you can do signed, unsigned, etc. Another thing you can do is, for example, maybe you're trying to create a counter or something like that. Doesn't necessarily have to be a counter, but you can do fun stuff like this. So that would take your input 8, add 1, and then you have your output 4. It's pretty simple. With the unsigned and signed, you can add or subtract integers from them. So you don't necessarily do addition, you can do that, or you can even do multiplication too. So it's pretty easy. You just have to get used to them, basically. So for simple addition and subtraction and everything, that's pretty much all you need to know. Other than this, one last thing. And then VHDL, you can see all these are 4-bit vectors, 4-bit buses. In VHDL, 2 4-bit additions will give you a 4-bit output. If you want to do like a carryout or something like that, it's really quite easy. Is create another set of signals here real quick. So let's say you want to have the carryout. So the quote-unquote easiest thing simply take your number, take the most significant bit, do a concatenation with the actual signal. There you have a, oops, it should be 4 here. You have a 5-bit number here. You have a 5-bit number on the left side of the addition, and then once we copy and paste this, you'll have one on the right side too. So, well, this is for unsigned, you could just, let me change this real quick. For signed, this is what you would do. So, because you need the most significant bit. For unsigned, you would simply, actually here, let me do one more example with this real quick, just to do everything in the right order. So, there's also another way to do this. Everything, there's 50 million ways to do it, but so basically it's pretty simple. You simply do the signal and left. That will give you the leftmost bit index. So that's essentially the exact same thing as this. Oops. And then put 11. So you may be wondering, why would someone be doing this, since this is actually shorter? Is it, let's say you're working on your code or something like that, and someone said, oh, I want these to be 5-bit numbers with a 6-bit output. For this example, you can simply just change that. You're hunky-dory. Everything's going to be, compiled and everything like that. For the previous one, if you change it here, example this will give you the wrong output. You have to go in and change these. So, you can do it either way if you're doing this sort of stuff. Just make sure you keep everything straight. This, I think, is harder to type but easier to work with later. You're less prone to make mistakes, but obviously up to the person actually doing the coding. So, one last example with the math libraries. So, if you wanted to do it unsigned, since unsigned numbers, a little bit easier to sign extend. Oops. This is all you do. Oops. So, it's not complex or hard. All you're doing is just adding a 0 at the beginning of the number. So, it's pretty easy. It's not hard. So, it's just for signed, you have to make sure you couple do the most significant bit. With unsigned, you just add the 0 in the end. So, that's a big bunch of examples, but goes over most of the cases for addition. Likewise, subtraction is the same thing. So, you can do multiplication with these. Obviously, I'll just do one example real quick. Why am I typing this? So for multiplication, as you guys hopefully should know, I don't know if you've gone over it in class yet, but you need double the sum of the widths of the buses or vectors, and the output is you have in the input. So for this, it would be input 15 times input. That's all you do. It's not complex or hard. Let's say you wanted one of these to be a 5-bit input, and then you just simply change that to a 9-bit. It's pretty simple. It's just simple logic. So, actually, since these are after the begin, they should be indented. So we have to have nice indentation. So, that's for the most part all there is to the numeric libraries. They're extremely helpful if you're doing math or anything like that. So, and there are older ones, but I would not suggest using those. Those are being deprecated, so you really want to use the numeric libraries, not the old ones that are tool independent, or dependent, I should say, and all that fun stuff. So just use the IEEE numeric libraries and you're good to go. Now, for the second part, which will be how to do flip-flops, registers, etc. like that in VHDL. So, first thing is that almost always flip-flops are done with behavioral. I don't know. Let's see. In all the code I've looked at, let me put it this way, I've never seen one done structurally. So, let's go over a quick little example first. So, clock event, and it's basically, this is true when you have clock event, basically. So either it goes from low to high or high to low. Whenever that happens, this will be true. And when you have something like this, that means whenever there's an event and clock is equal to 1, which may seem a little convoluted, but basically it's saying the rising edge. If you want to do falling edge, simply change that to a 0. But we want to do rising edge, at least for this example. So, we have when there's a rising edge, you can simply say, let's say, I'll just be going over using these signals just because it's easy. So, that is your simple flip-flop. No enables, no clear. Simply when there's a rising edge, the input gets written to the output. It's pretty simple, and everything like that. So let's say you want to add a synchronous clear and enable. So you have if clear is equal to 1, then so pretty simple example. Basically, clear is equal to 1, you clear it. If clear is equal to 0 and then enable is equal to 1, you simply have the input going to the output on the rising clock edge. So it's a standard, synchronous D flip-flop with, D flip-flop with synchronous clear. It's pretty easy. But one thing I should mention is that since processes are evaluated sequentially, even though they're done in parallel, it's sort of a weird thing, but for this rising clock edge here, if you were to put enable here, if enable was 1 and clear was 1, it would just do the enable. So if both of these are 1, it does this top one right here. So it just says, oh, clear is equal to 1, we clear it, we're good to go. Likewise, if enable was up here, it would take precedence. And it would assign the input to the output and it wouldn't clear it. So for these things, the order matters. So that's just something to remember. Order matters inside processes. So, actually I have a syntax error. So, forgot that. And I think I've told some people in the class this, but when you're debugging VHDL, sometimes one error will cause multiple other errors. So, what you probably want to do is when you're writing VHDL, and you save it and you see errors, always go to the very first error, fix that, then work your way down. Simply because sometimes what will happen is you'll fix a single error and like 30 more will pop up. Sometimes you'll have 30 errors, you fix the first one and that will clear out all the others. So you need to make it's really helpful generally to solve the first error first, because the parser is, once it sees an error, it'll try to keep on going. And sometimes it'll find errors that aren't there after that first error because it propagates. So, just a quick side note there. So, we've gone over the basic flip-flop one with clear and enable, synchronous clear, I should say, in enable. So let's say you want to do an asynchronous clear. So, asynchronous clears are just simply clear, whether it's a block event or not. Rising edge, I should say. Oops, what am I doing? So basically here, you're saying clear is equal to 1. Output is cleared. Then you have the else if. Like that. So, anytime clear is high, the output goes low. Doesn't matter if it's a rising clock edge or not. Otherwise, if there's a rising clock edge and enables 1, the input goes to the output. Let's say you just wanted to have a standard flip-flop with a clear, but not an enable. Simply just do this, do that, and you should be good to go. So, flip-flops are pretty easy to do in VHDL once you know how to do them. They're not complicated or anything like that. You just have to know how to actually write them. So, there are some idioms in the slides I have. So if you want to see more examples about flip-flops, you can look in the idiom section, though I think there's 2 or 3 examples, and you can look at those. Likewise, this is a very, very common thing, obviously. So you can Google it and find tons of stuff too. Not sure everything will be right, but you can find tons of stuff on Google. So that's another thing. And one last thing is, also in the slides, in the references, I think it's SynthWorks or something like that, I forget exactly. But there are a set of slides that have to do with math. Those have been very helpful back when I was internship for a company doing stage controller work, which obviously had a lot of math and controlling, like control stuff, PID, stuff like that. I use those slides a lot. So when I was learning it and everything like that. So those slides are definitely worth looking at. This is just a very brief overview of some stuff. If you want to go into more detail, definitely find those slides. They're very helpful. And I think that's it for now. So thank you.